Good afternoon. I'm very pleased to be here at the Royal Institution to give this set of Christmas lectures on the planets. This is 150 years after Michael Faraday gave his first Christmas lecture, and there's a distinguished scientific tradition at the Royal Institution, which I'm very pleased to play a small part of. My topic is the planets. We, of course, live on one. It's called the Earth, and it is a tiny little planet made of rock and metal with a tiny, thin atmosphere around it, clouds, water, rocks, mountains, and life. And one point of interest is to what extent is this the case on other planets? To what extent are things there different from here? This machine is called an orrery, and it is a kind of mechanical device to show how the planets move. There were lots of them made a few centuries ago, not so many these days. The brass sphere in the middle is supposed to represent the sun, and if I turn this crank, you can see the planets moving. The innermost planets moving very fast, the outermost planets moving extremely slowly. The fastest moving one here is Mercury. The next one is Venus. This one here is the Earth with the moon next to it. Then Mars, Jupiter with 4 of its 12 or so moons shown. And then over here, Saturn with its rings, and 5 of its 10 or so moons shown. Beyond Saturn, except it would be too big to fit on this orrery, are the planets Uranus, Neptune, and Pluto, and perhaps even some others. There's been a recent discovery of a tiny little planet out here between Saturn and Uranus. Perhaps it is a single small planet, or perhaps it is one of a great horde of little planets which might circle the sun out here. There is a horde of small objects which circles the sun between Mars and Jupiter, called the asteroids. We are just beginning to explore the planets. We are only in the earliest stages of understanding them. And I would like to begin by giving you a sort of bird's eye view of some of them. The first picture here is intended for orientation. We're on this third one, and you can see what a tiny and insignificant planet it is. And the solar system is mainly these large planets in the outer solar system. We are on the debris, the little tiny chunks of incidental matter in the inside of the solar system. Now, people have long dreamt of traveling from one world to another. There are various methods of doing it. This is one suggested by a French artist named Grandvie in the last century. It's a lovely way to do it if only we could figure out how to build the bridge, but we haven't figured that out, and our method is quite different. It's to send a spacecraft from the Earth to the other planets. And the other objects in the solar system are really quite nice. This is a photograph of the moon. You can see the dark, smooth lowland regions. The bright, this is music for this occasion. It is Japanese shakuhachi music, and why we're using this music I will say in just a moment. The bright, rough areas of the moon are highlands, and you can see that there are holes or craters which pit the moon and they are produced by the impacts of large objects falling from space throughout geological time. The solar system is very old, 4.5 billion years old, and the scars of early catastrophes still exist on the lunar surface. A close-up view of the lunar surface shows not just craters, but also this remarkable, wiggly, sinuous rill whose origin is still being debated. There are many craters. Here is a close-up of one, and we will, in a later lecture, not only talk about craters, we will make some in a generally non-destructive way, and we will not harm too many people as we make a crater. This is a very large crater, the one you just saw. We will make small ones later. There are craters not just on the moon. Here is a mosaic of photographs of Mercury, and this detail was not known until very recently. This is the result of the Mariner 10 spacecraft to Mercury, and you can see a great deal of detail, but again including craters. If we move outward from the Earth, we come to the planet Mars, which we see here in a lovely Viking photograph. And here, the big craters that you see are not made by impact, by collision. These are volcanic craters. Mars has, among many most interesting features, extraordinarily large volcanoes, the largest of which is almost 30 kilometers high, 80,000 feet high. That is a very large volcano. Mars is a lovely, beautiful, interesting world, in some ways very much like the Earth, in some ways extraordinarily different, and we will devote a few lectures later on to studying Mars. Beyond Mars, we leave the terrestrial or Earth-like planets and come to the first of the great gas giants, Jupiter. Everything we're looking at here is clouds and atmosphere. If there is a surface to Jupiter, it is far below the region we can see. The weather or meteorology on Jupiter is very different from the Earth, very interesting, will teach us much, as the studying of all the planets will do, about our own planet. Jupiter has a number of moons. What you are seeing now are the very best Pioneer 11 photographs of one of the moons of Jupiter. We can see almost nothing at all. And this is the best picture we have at the present time. In 1979, two spacecraft called Voyager will pass very close to the moons of Jupiter, and we will obtain 50,000 photographs of Jupiter, Saturn, and their 20-some-odd moons, and we will have turned our almost complete ignorance about these moons into great knowledge. These moons, by the way, are not like our own. Some of them are icy, some of them are covered with sodium and other salts, as if there was a great ocean which was lost into space. These are very strange places, and they will be very interesting to explore. Beyond Jupiter and its moons is Saturn, the great ringed planet. The nature of the rings is something we'll say a word about later. The Voyager spacecraft will also pass by Saturn and its rings. It will, in fact, then pass perhaps by Uranus, if it is still working, and will inexorably leave the solar system. It is condemned to wander forever in the dark between the stars. Its transmitters will eventually die, and it will be silent, but still the most distant emissary of mankind. We thought that in the remote chance that there are other beings on planets of other stars who wander between the stars and capture derelict spacecraft from backward civilizations like ours, that it might be nice to send a message. And so there are phonograph records on each of the two Voyager spacecraft with instructions for use, written not in English, since it's unlikely they speak English. And those records contain some spoken and written greetings, a great many photographs, scientific information, sounds of the earth, some greetings from whales as well as people, and an hour and a half of the music of the world, among which was the Japanese shakuhachi piece that you just heard. So we are, in a very preliminary way, trying to say hello to the cosmos. Now, on the outskirts of the solar system, in fact, halfway between here and the nearest star, are the comets. They are the closest thing to interstellar matter that we are likely to be able to examine in the near future. They are an almost complete mystery and another major objective of space exploration. Now, this picture of the solar system is relatively recent. For most of human history, people thought that the Earth was at the center, not just of the solar system, but of the universe, and that not only all the planets went around the Earth once every day, the Earth was not imagined to rotate, but also the sun went around the Earth. And that was a kind of astronomical egotism in which we thought we were splendid and all the other objects in the universe somehow secondary to the Earth and its inhabitants. Well, what we have found is just the opposite, that we are a very humdrum and ordinary locale in the universe. And one way in which this was found was to consider the question of the phases of the planets. Now, we know that the moon goes through phases. We see full moon, half moon, quarter moon, crescent moon, new moon. But what about the planets? Now, in the old Earth-centered view, thank you, the planets, in this case Venus, were imagined. There's a lovely old book which has moving parts, unlike books today, which only accidentally have moving parts. This one is moving on purpose. Venus was imagined to go around the Earth, but also to have a little internal motion of its own. And that view, with the sun out beyond Venus, made a certain prediction about the phases of Venus. You would sometimes see partly illuminated Venus, sometimes see a full illuminated Venus, but no one had a telescope to see whether Venus went through phases, and if so, what kind. Now, here is the Earth-centered view of the universe, with the Earth here and the planets and the sun going around the Earth. This is the supposed orbit of the sun. And in the sun-centered view of the universe, the planets, including the Earth, go around the sun, and as this old picture shows, go through phases. Well, in the sun-centered view, or hypothesis, let's try and see what the phases ought to be like. What I'm going to do is to have someone be Earth and someone be Venus, and I will try to be the sun, and just because somebody big has to operate the light. And let's see what the phases of Venus would be like. So could we have an Earth person? Thank you. This is an excellent Earth person. And could you please stand by, let's say, a few steps up, by that camera, and we will be eventually viewing things on the television screen from the point of view of that camera and that Earth person. And now could we have a Venus person? Venus is a planet completely covered with clouds, although it's a very nasty place on its surface. And so we have this completely clean sphere representing Venus. And could you just stay there for just one moment? And what I'm going to do is point this light representing the sun at Venus. Now, if this were a real sun, it would be shining in all directions, of course, but then everybody in the audience would be blinded by the light from this, and you couldn't see what was happening here. So I'm going to simply follow the motion of Venus around the sun as seen from the Earth. Now, the Earth really ought to be moving around the sun also, but that would be a little awkward, and the Earth would have to step over people's knees and so on. So we're having the Earth stationary, but the point will still be made. So now, Venus, could you please slowly circle the sun? You can do it a little faster than that, actually. It takes Venus 225 days to go around, but we will do it somewhat faster than that. And now notice how we are going into half moon, or half Venus, crescent Venus, and now Venus is passing by the sun, and now the crescent comes around again, and Venus is now nicely walking backwards into a half Venus, and now growing, the phase grows, and soon we will be back near full Venus. Thank you very much, Miss Venus. Thank you very much, Miss Earth. Now, that kind of motion is exactly what Galileo found Venus to do when he looked at it with the first telescope several hundred years ago. And Galileo found that the waxing and waning, the changing from crescent to full, back to crescent, of Venus did exactly what the sun-centered hypothesis predicted, and not at all what the Earth-centered hypothesis predicted. And that's one of the lines of evidence that the Earth is not the center. Now, if we actually look at a picture of Venus, we see that it does go through phases. This is a telescopic view of Venus, and I just show you this so you will believe me if I say Venus goes through phases. Actually, the Earth also goes through phases, and in this picture, there's a lovely picture of the Earth as seen from the moon. The moon is in the foreground, and the crescent above the moon is the Earth as seen from the moon, and it goes through phases, if you figure it out, for just the same reason that Venus or the moon does as seen from the Earth. Now, this is the geometry of the solar system, but we haven't said anything about scale. How big is it, the solar system? There are lots of ways of finding out, the simplest of which is by radar. You send a radar pulse to a planet, it hits the planet, comes back, you measure how long it took, you know how fast radio or light travels. It travels at the speed of light. And, right, that was easy. 186,000 miles a second, 300,000 kilometers a second. And so half of the transit time gives you the distance. And in this way, we can determine, for example, that the Earth is about 150 million kilometers, 93 million miles from the sun. I hear an echo, which we're not supposed to hear quite yet. And what we'd like to do is to give a sense of the scale of the solar system by having someone in the audience say something like, let's say, hello, universe. Seems an innocuous enough remark. And let us see how long it takes for that remark to get to various places, starting with the moon. Who would like to say hello to the universe? That's good. Lots of people would like to say hello to the universe. So would we. That's why we sent the Voyager record. Could you please say hello, universe?
Hello, universe. Hello, universe.
Aha. Now, that was a 1 1/4 second time delay, which is, by accident, just how long it takes for light, or radio, to travel from the Earth to the moon. Now, we have here a diagram which has just been started out to indicate the rate of progress of a signal sent by radio from the Earth into space. So here's the orbit of the Earth, and we will see how long it takes for that signal to get to the orbits of the other planets, Venus, Mercury, the two interior planets, Mars, the next planet out. Here's the Sun, and Jupiter and Saturn will be out here. And so in the next few minutes, we will follow the progress of a radio signal. And this is the fastest that anything can travel. So what we are going to see is the fastest travel time that is possible. Now, what I would like to do now is to, while we're waiting for the light to get to other planets, to begin a discussion of a particular planet. We would like to study in some depth a strange and exotic world. Let us imagine that we know nothing about this world, that we have no prior information about it, and we approach it with absolutely open minds. We have no prejudices about whether it's inhabited or not, whether there are volcanoes or rivers, or if there are inhabitants, what they look like. Maybe they are all squamous, blue ovoids with 30 tentacles and float 1 meter above the ground. Or perhaps that's what we look like. Perhaps we're from some other planet, let us say. And we will examine this distant and exotic world, which by accident is the Earth. And first, we will look at it from telescopes from our world, and it will be little, and we will not see much detail. And then we will come closer and closer and look with... we just heard another hello universe because our radio signal has just gotten to Venus. And we will shortly be interrupted by another hello universe when it gets to Mars. It's just reminding us of the progress of our radio message. We will look mostly with photographs, first from our planet, as I said, then we will put cameras on imaginary spacecraft which will fly by the Earth, then go into orbit about the Earth, and then land on the Earth and look around and see whatever is to be seen. Now, in addition to looking, we can use scientific instruments to determine other factors about a planet. For example, we could pass the sunlight reflected off the planet through a device called a spectroscope, which divides the light up into individual colors or wavelengths. And if there are colors or wavelengths missing, subtracted by the passage of sunlight through the planetary atmosphere, we can, by appropriate laboratory comparisons, determine something of the chemical composition of the atmosphere of the Earth. And we would find that it was composed of nitrogen and a rare and poisonous gas called oxygen, some carbon dioxide, some nitrogen, small amounts of water vapor, ozone, some other gases. All of that could be determined remotely without ever going there. Hello. It has just reached Mars. Another thing we could do, we know how far the Earth is from the Sun. We know how much sunlight is absorbed by the Earth. We could calculate how hot the Earth ought to be from the sunlight which reaches it. We could test that idea by putting a heat-sensitive device, a thermocouple, say, at the focus of a large telescope and see how much infrared or heat radiation the Earth gives off to space. And in that way, we could begin to get some idea of the physics and chemistry of the Earth's environment. Well, I'm going to now begin this exercise, and I would ask you, oh yes, Mercury, it's just reached Mercury, is it? Yes. And I would ask you to pretend that you do not come from the Earth. You are from somewhere else. You don't know about the Earth. You wish to find out. Well, here's our first view. It's not very much. Hard to tell much about the strange planet Earth from this view. We see a half Earth. We already know it goes through phases. We see white with some patches. It is, in fact, the clouds of the Earth that we see. The Earth is, on the average, about half cloud covered. We obviously have to have much better observations in order to determine more about the Earth. Occasionally, we find the Earth in a strange locale, in this case, just passing in front of the sun. It makes for a very beautiful picture. Does not tell us much about the Earth. The Earth is the completely dark thing in the foreground, which is almost obscuring the sun. As we get closer to the Earth, we can observe more detail. Here you can see the wispy, lovely cloud patterns, and you can see that on the average they do cover about half the Earth. We can see down at the bottom the Antarctic ice cap. We can see a continent underneath the clouds. That is, the clouds come and go, but underneath them are features which don't seem to come and go. The continents are the same every time they appear over the surface of the rotating Earth. And there are also dark regions near the continents, which eventually we would discover were oceans. And that would be very strange, because nowhere else in the solar system, at least today, are there oceans. And if we looked in the extreme upper right-hand portion of this picture, we would see the Horn of Africa, the Arabian Peninsula, the Sinai Peninsula. There would be no sign, for example, of tank battles in this region. And the reason for that is that our resolution, our ability to see fine detail, is only about 100 kilometers in this picture. We could not see anything smaller than 100 kilometers across. And therefore, if we were to see a tank, it would have to be 100 kilometers long. And that is a very large tank, which fortunately does not exist on the Earth. So to examine more closely, we must get better pictures. And here we see a close-up of the same region. This is the region of the Nile Valley and the Ismaila Canal. You can see this beautiful cloud which runs from lower left to upper right. It is a jet stream cloud. You can see lots of wispy clouds. At this point, our meteorologists, our experts in weather, would start getting very interested. Our geologists, our experts on the surface features of the planet, would get very interested. Our biologists would be dreadfully bored. They would not see anything of interest, no hint of the Earth being inhabited, although they might argue that liquid water was good for life. There would be others who would dispute that. Here is a lovely picture of a cyclone, which would make our meteorologists extremely happy. They would study this picture for a long time. Here, well, there's a strange object in the foreground, which I ask you to ignore. That, of course, would indicate the presence of life. This is a Skylab spacecraft, but again, underneath it, all sorts of little wispy clouds. Here is another incidental spacecraft in the foreground. This is Gemini. Again, by the way, look at the edge or limb of the Earth. You can see this little blue band following the horizon, and that is the atmosphere of the Earth seen edge on. The tall stick with a cylinder on top of it is the means by which astronauts communicate to the ground. I sometimes like to think that it's an old tomato soup can connected to Houston, Texas by a long string, which you can see a little of. The other end of the string is another can, and they talk to each other that way. The trouble is that the string gets wound around the Earth many times, and it becomes a little awkward. That's not actually the way the communication is done. It's done by radio. That's the radio antenna. But it just looks like an old can on a string. That's all a parenthesis I couldn't resist. Let's go back to our extraterrestrial guys. Here is a lovely volcano. We are looking at the volcanic caldera, the hole in the top of the volcano, which you see, this dark thing right there. This is, in fact, the island of Hawaii, and is alleged to have a great deal of life on it, but you can't see anything of it here. All you can see is a volcano. Here's another volcano. I think this is Etna, and again, much the same situation. Beautiful mountain, no sign of nearby life. And here is another sign of geological activity. On the left in color is the San Francisco Bay Area and the Great San Andreas Fault coming down from the bay, which is a sign of great geological activity. There are many earthquakes there. In fact, eventually, California will drift out into the Pacific Ocean because of a split or tear along that line. Now, that will not happen soon, in some people's minds, regretfully, but will happen in the next few million years. Also in that picture on the right is another similar feature, the great East African Rift Valley, which is beginning here at the Dead Sea and goes all the way down to South Africa. It is 5,000 kilometers or 3,000 miles long and is a sign of great recent geological activity on the Earth. When we look at Mars later, we will find that there is a perhaps similar feature there. Here is a crater in North Africa. Perhaps it is of impact origin, perhaps not. Such craters are formed on the Earth as on the Moon, but the Earth has very efficient erosion. Wind and water rub things out. And for that reason, we have at any given time very few craters, even though big rocks fall from the sky on the Earth about as often as they do on, say, Mercury or the Moon. Here is, in the Arabian Peninsula, a set of lovely Sif sand dunes, which it would be one sign of evidence that the Earth's atmosphere is active and stirs up material and makes sand storms. Once we knew something of the atmosphere of the Earth, we could deduce that indirectly as well as this direct evidence. Notice all this time there's not a hint of life. We're looking at the Earth reasonably closely. We're looking often at kilometer resolution. We're seeing things a little more than half a mile across. And yet, in all of these pictures up to now, there hasn't been a hint of anything alive. Nor in this picture. You can see at left a lovely snow has happened in this mountainous region. To the right, you can see the mountainous region without snow. These are, in fact, the Rocky Mountains in the United States in the vicinity of Denver, Colorado. Here is part of the St. Lawrence Seaway in Canada, and you can see great floating blocks of ice breaking up. This is one of many pictures that would indicate the presence not just in oceans, but inland of liquid water. Here is a beautiful picture of ice-choked, sinuous rivers in the Arctic. And this picture, as many others, show the Earth to be extraordinarily beautiful. And I think long after our scientists got totally bored with the Earth, our artists would continue to be interested in it. Here now is a close-up picture of a particular river. You may see two numbers, a 5 and a 6 on the Earth. They have not actually been written on the Earth. That's just been put on for another reason. We should ignore that. If we saw a large 5 on the surface of the Earth, that would suggest that there was life on the planet, of course, especially if we used Arabic numerals. But what we see is this sinuous, tributaried, wandering feature, which is a characteristic feature of flowing liquids. And we can also look at the mouth of this river, the Colorado River. The mouth is up here at the center. And follow, yes, here's the mouth of the river. And we can follow the entire course of the river. By the way, in this picture, there is, right within the box here, a sort of corkscrew on the ground, some miles long. And it looks very strange and perhaps artificial. We might think that perhaps that was produced by intelligent beings. Turns out, not in the least, that's an old stream valley. Here now is a photograph of the east coast of the United States at kilometer resolution. And if you look closely at, say, New York City over here, or at Washington, D.C. over here, you find no sign of life, intelligent or otherwise, at kilometer resolution. You do find that the cities are discolored. The places where there are cities turn out from orbit to be dirty. But it would be a very intelligent extraterrestrial who would deduce that wherever there's dirt, there's intelligent life. And apart from the fact that cities are generally dirty, there's no indication of the existence of cities, much less their inhabitants, at this resolution scale. Now, here's a picture which clearly shows the presence of life, if only we were wise enough to recognize it. Because each of these peculiar Pacific islands is a coral atoll, is a product of life. That one, say, or that one, or this one over here. They are produced by colonial organisms, coral, hordes of animals all working together to make a coral island. But unless we know beforehand about life on Earth, it would not be apparent that that's the case. So here's a sign of life, but we wouldn't recognize it. Now here is the Salton Sea in California, and just below it, a region called the Imperial Valley, which in this picture gives a sense of structure. There's a kind of mottled pattern there. If only we could see it better, we might know something about what it's like. Well, we can look more closely, and here, if we look still more closely at this red patterned ground, we have a sense of structure, of squares and rectangles, just barely apparent. If we look elsewhere, at improved resolution, we find that the Earth is covered with squares and rectangles. When we look at the Earth at 100 meters resolution, there are squares everywhere. For some reason, the Earth is into squares. Now, there is no way that this could be of geological or meteorological origin. These squares could only be of biological origin. And so we would have to deduce that there's some strange form of intelligent life on the Earth which is passionate about carving the ground up into squares and rectangles for reasons which we cannot in the least imagine, but there's no doubt that that's what it likes to do. And so now we must make a search for the square people. Here, this is a place called Chicago. Different kind of squares and rectangles are apparent here. What their function is, not so obvious. This is Denmark, where they're more into rectangles than into squares. It's a nice departure. Here is France, where the arrangement is not nearly so regular, and also each pattern is separated from the next one by a dark line, which is in many cases due to hedges. So here we have not just a passion for Euclidean geometry, but also a passion for territoriality. And here is still another pattern. This place is into rectangles, but is also into up. In this place, great structures have been built vertically as well as horizontally. This is New York City. And how these stalagmites of intelligent origin ever came to be would not be apparent to us, much less why they would want to build up when there's so much unused ground to build sideways on. There would also be vast engineering constructs which would be apparent to us. This is the great Arecibo radio telescope in Puerto Rico, about which we will say more in a subsequent lecture. And now here is a candidate dominant organism on the planet. Each of these is a creature which, for sake of definiteness, I will call an automobile. And here is a great horde of these intelligent organisms, all clustering together, perhaps for warmth, or perhaps it's an outdoor political rally, or maybe a religious revival meeting. And one can, in fact, see that much of North America and Europe is constructed for the sake of these little organisms. Great straightways which are designed for them, and there are special buildings to which they go at night in ones and twos. And occasionally one can see small automobiles, which are obviously the young. And at this point, we would assuredly think we had found the dominant organism. But if we looked closely, we would see that there were small parasites which would come in and out of the automobiles. And we would think that we were now into the microbiology of the organism, disease organisms, and we had made great progress, little imagining that the real dominant organism had yet to be found. we would be quite astonished by a picture such as this, in which there are great organisms, many tens of meters long. Every one of these little white things here is, in fact, a great whale. And this is a picture taken in the ocean. And then we would see places like this. This is a marvelous sand dune field. And in these great sand dunes, we would see strange creatures like these. And what could these be? Well, we would have the following kind of argument. We would say, look, in this place there are stilted lumps. There's lumps about that size connected to the ground by 4 stilts, and many of them stretching as far as we can see. Now, how do you make stilted lumps? Well, there are no weather ways to make it. There don't seem to be any geology ways to make it. Probably it's a biology way to make it. Not only that, things get rubbed down on the Earth. There are sandstorms which rub things down, running water rub things down. And we could calculate that in a period of only a few thousand years, the stilts would all be rubbed away and the lumps should be on the ground. So these stilted lumps have been made in the last few thousand years. There's some machinery on the Earth for making stilted lumps at least every few thousand years, maybe much faster. And I think we would have to deduce that that was due to biology, and perhaps these are the dominant organisms. Then we would look closer. Here is a set of interesting creatures which would then be gone about 2 minutes later. This is in fact a flock of flamingos. And if we now look at another picture, here we have for the first time the organisms that we truly know to be the dominant organism, human beings. This is a great outdoor swimming pool. Each dot is a dominant organism. And nearby there are blankets, and on each blanket there are 1 or 2 dominant organisms. But to see what the dominant organisms are really like, we would have to go still closer. And if we really did that, we would finally come to grips with the true nature of the dominant organism on the planet. Now, I'd like to do just for a moment, a stepping back. And let's examine still another picture. We have up to now looked only at the Earth in reflected sunlight. Here's the Earth in emitted light. Up at the top we see, this is North America, up at the top we see a very bright light, which is in fact the aurora borealis. But down here, all these other lights are due to cities at night. Here, for example, is the New York to Washington corridor, and so on. So the Earth, due to its intelligent life, shines at night. Here is a remarkable picture made of the Earth in radio waves. It shows the Earth emitting to space in radio radiation. And look, the map is exactly like in the geography books. And the people who wrote the geography books were never in space. So they did a very good job. And here, this is part of a plaque on a long-lived spacecraft. And here we have the configuration of continents some 200 million years ago when they were all almost together and touching. Due to what is called plate tectonics or continental drift, the continents move apart. Here is their present configuration. And some 8 million years from now, here's what the continents will look like. Britain seems to be still here. Italy seems to be missing. Seem to be a lot of new places in the Indian Ocean. And as I mentioned, over here, you can see California having drifted out to sea. That's merely to mention that the configuration of the continents of the Earth is true only for now. At another time, it'll be quite different. Now, to show some familiar geography, you may recognize these small islands. Picture taken from space with a configuration quite like that in the geography books. And let us do now another zoom in. In this case, let's try to zoom in on some places that most of you know. Here you can see England in the rough vicinity of London. If we look more closely, we can see the Thames estuary. I may have this upside down. And the Thames in the vicinity of London. And then if we look still more closely, we might see some more rectangles, London rectangles in this case, some strange buildings, one particular domed building in central London. And if we then zoom in to this strange building, we can perhaps pick out a random dominant organism in London. There are some dominant organisms now. So we have now done twice a kind of exploration of the Earth and seen, among other things, how varied and interesting it is, but also how difficult it is to look for life. It is not easy to find life. You have to look very closely on a planet to find life that's there. Now, maybe I can have a globe of the Earth. Thank you. All of the things that we've been talking about are on, in the last few minutes, are on the surface of the Earth, and they are conveniently put together in globes like this one. And on this globe, there are national boundaries marked, but on photographs of the Earth from space, there are no national boundaries to be seen, which is perhaps a useful lesson for politicians. The Earth rotates from west to east so that the stars can seem to rise in the east and set in the west, otherwise it would be difficult to explain them. And as it turns in this way, some parts of the Earth plunge into daylight and others plunge into night. And you can imagine, for example, a wave of toothbrushing which circles the Earth once every day at the terminator, the place where light and dark parts of the Earth meet. There are actually two such places, but I'm talking about the morning one. Well, we have so far been talking mostly about the solar system. By now, our hello universe signal has passed far beyond the orbit of Mars, far beyond the sun, which is lovely yellow, as you see. But if that original hello was given, say, half an hour ago, the hello is just now something like reaching Jupiter. How long before it reaches the nearest star? That will take another 4.5 years. The stars are astonishingly further away than the planets. So all we've been talking about is a cluster of little worlds around the sun, and then some immense distance to the nearest star, which may indeed have planets about it. How is this discovered? How is it known how far away the stars are? We cannot bounce radar off the stars. It has to be done by some other method. And let me just give you briefly an idea of how one of the early, very clever minds in astronomy figured out the distance to the stars. This is a man named Christianus Huygens, who lived in Holland, thank you both, in the 17th century. And he argued as follows. He said, "It looks to me as if the stars are suns. The sun is near, that's why it looks so bright. If the sun were some immense distance away, it would be just a little pinpoint of light and seem very dim. How far would I have to move the sun away in order to make it as dim as some bright star at night, let's say Sirius?" So Huygens went out at night and looked at Sirius for a while. Look, look, look. Remember how bright Sirius is. Then, next day, still remembering how bright Sirius was yesterday, he went out and looked at the sun. He had a brass plate, painted black here so it doesn't shine badly to the television cameras. His was shiny. And he held the plate up to the sun and looked through each hole until he could find a hole which was so small that the amount of light from the sun which entered was just as bright as he remembered Sirius to be last night. And then he happened to know the inverse square law, which I hope many of you know, and was able then to calculate how far away you'd have to move the sun. And he came out with the answer of about half a light year. That is, it would take light about half a year to go from here to Sirius. Had Sirius, in fact, been intrinsically as bright as the sun, he would have gotten exactly the right answer. In fact, Sirius is brighter, so he got it a little bit wrong. But he came very close, within a factor of 10. And it's an astonishing achievement that Huygens did. And it suddenly made a universe vast and awesome beyond ordinary human understanding. Many people like Pascal said that they were frightened by the great spaces between the stars, because space is amazingly empty. Now, I would like to close with a little discussion about the nearby stars. When we look out at night, we see the constellations. Many of you have probably been forced to memorize certain patterns of dots as if they were somehow firmly embedded in nature, as opposed to arbitrary psychological projective tests forced on innocent children by astronomers. So, for example, many of you know what I call the Big Dipper, and you know as, I think, the Great Bear or the Plow. Look at that. In America, we think it's a thing that you pick up liquids with, and in Britain, you think it's either a bear or an agricultural implement. Now, those are three quite different things. That must be merely what's in people's minds and nothing to do with what's out there. Now, what is a constellation? Constellation is a configuration of dim but nearby stars, bright and more distant stars, which by accident happen to be in the same part of the sky when you look up. Now, I've been so annoyed at this business of forcing everybody to learn constellations that I've made as strong an effort as I've been able not to learn the constellations. So I know only a few, and those only by accident. I didn't mean to learn them. One of them I learned for this sort of lecture. What I've always wanted to do is to find some new constellation and give some absolutely silly designation to it and make everybody have to learn that. But that's hard to do because all the constellations have been named. The ones in the southern hemisphere more recently, so you'll find the constellation of the microscope and the constellation of the telescope. And I guess if they had been discovered still more recently, you would have the constellation of the refrigerator and things of that sort. Well, there are no new constellations to be discovered around here. What we have to do is go to some other place where the constellations are different, and no human being has named them yet. How far away do we have to go? We clearly have to go some distance comparable to the distances between the stars themselves. We must go many light years. A light year, the distance light travels in a single year, is about 6 trillion miles. It's a big distance. Now, we can't yet do that. Voyager is, in fact, on its way to the stars, but it will take some 50,000 years to go the distance to the nearest star, and that's a little sluggish for the purposes of this lecture. So what we can do, however, is to ask a computer, which knows the three-dimensional positions of all the nearby stars, to draw us a picture of what the sky would look like from this place or that. So let's start out looking at such a picture, first from the standpoint of the Earth, so that we can see some recognizable objects. So here we have the constellations as seen from the sun. These are in the northern hemisphere. And this constellation right here is the Dipper, Bear, Plow. Maybe you can see the handle of the Dipper in the bowl here. I guess this is the body of the bear and the tail. And I can't see how that's a plow. Maybe that's the plow and that's the reins, and there isn't any horse, maybe. Anyway, everybody knows that constellation. Even I know that constellation. And over here is the North Star. By the way, all these nice dashed lines and numbers are, of course, not on the sky. If they were on the sky, that would make all of this much easier. But I would like to call your attention to this configuration, which is an up, down, as you can see. And it's called Cassiopeia, and as everybody can plainly see, that's a lady sitting in a chair upside down in the sky. Now, let us ask the computer to look at the stars in the same region of the sky, but from the vantage point of the nearest star, a place called Alpha Centauri. Well, when we do that, we see, thank you, here is the Big Dipper, Plow, Bear, exactly the same. Here is the North Star in exactly the same position. Why are they the same? Why aren't they different? Why haven't we changed our perspective enough to have the constellations change as well? And the answer is that we have not gone far enough. There's in fact only a single change in this picture, and that is in Cassiopeia. Here's Cassiopeia, and it is as before an up, down, up, down. The only difference is there's another up. There's a new star which wasn't there before. What star is that? It's the sun. That is our star as seen from Alpha Centauri. Of course, the sun is not in our night sky, because if it were, it wouldn't be night. That's the difference between day and night. So we have to go a bigger distance. So let us now look at the constellations from in the vicinity of the Earth again, but not in the northern celestial hemisphere, but in the broad range of middle celestial latitudes. And I won't ask you to memorize all of these stars, but in here are all the zodiacal constellations, what people ask you about when they ask you, what sign are you? I like to say slow school zone ahead, but what they mean is astrological signs, the sign of the water carrier, or the scales, or the lion, or the virgin. All of those are supposed to be in here. I can't see any of them. But what we can ask the computer to do is to move a distance, let's say, to the nearest star like the sun. That's a place called Tau Cetus. And ask it to draw the constellations in this part of the sky. And when we do that, we find that there are enough apparent motions of the stars that we get new constellations. And so I thought it would be fun then to finally put my exotic new constellation in the sky of Tau Cetus. And I thought I'd make up a constellation of the unicorn. But since there's already a constellation of the unicorn in our sky, I figured I'd make a special six-legged unicorn. So you'd know it was a fake unicorn, not a real unicorn, like the ones we have here. And I thought that the artist would do the 6 legs 2, 2, and 2, like insects on the Earth. But as you can see, what the artist did was a quite creditable 3 and 3. Now, the constellations are quite different here, and so I'm finally able to make my constellation of the unicorn. The sun is, in fact, a star in this sky, and by a strange accident, it is, in fact, that star right there. Now, I imagine that there would be some problem for the scientist who lived on a planet of Tau Cetus who proposed that there was life on a planet that circled the star which joined the unicorn's tail to its rump. It sounds unlikely. You cannot tell, just by looking at the stars, which have planets, which planets are inhabited, or anything of that sort. And as our last slide reminds us, there are an immense number of stars. There are, visible to the naked eye, only some thousands of stars. In this picture, there are perhaps 10,000 stars. But in the Milky Way galaxy, of which we are a part, there are some 250,000 million stars. Were we to move only 30 light years away, we would be unable to even see the sun with the naked eye. And that is 1,000th of the distance from here to the center of the galaxy. We live in a galaxy vast and awesome, beyond ordinary imagining. We live on a planet which seems typical, a star which seems typical, in fact, in a galaxy which seems typical. And the great question of questions is whether what we have here is indeed typical, or is it in some way unique? We will explore that in later lectures.